morning, everyone. Thank you for joining us today on our third Connecticut Smart event. Today, we're going to be talking about autonomous mobile robots in manufacturing. So a little bit of a agenda here put up on the screen. We're going to take about 15 minutes to give you an introduction and overview of the SMART-E program. I'm going to do a little bit of housekeeping. We are in CCAT Advanced Technology Center. We are an ITAR facility, so I do ask that you don't take any pictures. We have, if you would like to take pictures, we do have a couple of the CCAT folks around. You can ask me as well if you'd like to take pictures of something. We can take the picture and then send it to you. What we'll have is we'll have Nancy Tegway from DECD, the state of Connecticut, come up and talk about the particular program. This program is in partnership. We've got University of Connecticut and CONSTEP as well, supporting different aspects, and you'll hear more about that. As I mentioned, no photos. Restrooms are located. If you go out the left side here, out of that door, go all the way down and then take a left out of the doors. Just keep walking straight and you'll see two restrooms. It's really where you came in from the reception area and you look straight ahead. There's two doors there. You can use either one. Fire exits and assembly locations. So we do have a fire exit here. We've got another one back there. And if you go out this way, we have another one back there. Typically, we meet at the flagpole. So if we do have a fire drill, we do have to walk out of the parking lot, straight out of the building, and then turn left, and you'll see a flagpole over at RTX, and that's typically where we gather. And then at the end, you'll see a couple of QR codes or links. We'd love to get your feedback. We want to know how we did in these events. It's important for us to know if this is relevant for you or if there's some other kinds of technologies you'd like us to talk about and to demonstrate. So please do stay tuned for the end when you see that link. With that, I'm going to hand it over to Nancy Tegway from the state of Connecticut.
Thank you. Hi, everybody. Hi, everybody. My name is Nancy Tegway. I work for DECD. I am the program manager for CT SMARTE, and I just wanted to spend a couple minutes to talk to you guys about, talk to you just for a couple of minutes about this program. State of Connecticut has heard a lot from manufacturers in the state about a couple of things: competitive supply chains and also high electricity costs. We are very dedicated to solving these problems as best we can. So this is one program that we have started, and it's in order to help small and medium-sized manufacturers adopt smart manufacturing into their facilities and their manufacturing processes in order to reduce energy consumption and also meet the needs of their OEMs. We're doing this in a variety of ways. First of all, we are partnering with three great partners, CCAT, UConn, and CONSTEP. We are providing SMMs with improved pathways to support and funding to enable them to adopt the low-hanging fruit in the smart manufacturing world, which is facility upgrades, but also the more in-depth and more expensive opportunities in digital twin, digital thread, and more advanced technologies. We're doing that through offering energy and smart manufacturing assessments of your facilities through UConn's ITAC program. We are doing it through offering workshops and trainings such as this one hosted by CCAT. But in addition to that, we are, CCAT and UConn are both looking for demonstration projects. They want to work on projects for your companies if you're not ready to move into the smart manufacturing realm on your own. And some of these projects include in the digital thread realm, automated CNC programming, digital twin and machining optimization, autonomous part transport, autonomous deburring, AI vision, and see how smart vision leverages deep learning to perform visual inspection on your parts, and automated inspection. So these are just a few different projects that in order to spark your imaginations, we are here to help you learn more about those and bring those into your facility, do the work for you. We are connecting smart manufacturers with funding. I mean, this is money that's available to you. I know a lot of it is known to you, particularly the manufacturing investment funds. We have money from the Connecticut Green Bank. We have a new initiative in the state of Connecticut called the Strategic Supply Chain Initiative. We have the ITAC implementation grants, which is money to bring in some of the improvements and energy efficiency measures that the ITAC team discovers in their facility assessments. There are manufacturers assessments through CCAT's partners. And we also have money from the utilities. They are very willing and able to help support transition to energy efficient components and different products to help reduce energy consumption. That's kind of where we see our best efforts going. We can't reduce the rates, but we can help you use less. So essentially, benefits, product development, time cost, time to market, reduced energy consumption. Here are a few samples of how these things can help save time and energy. So it's adopting smart manufacturing means a lot of things to a lot of different people. So in order to be more specific, we need you to come to us and talk to us about what you need, and we'll create the right program for you. So by being here, you are taking the first step, which we appreciate, and hope that by scanning this QR code, you'll get in touch with a member of our team. Other news out of the Office of the Clean Economy and the Office of Manufacturing of the state of Connecticut, with which we are associated, we have a new Chief Manufacturing Officer who is replacing Paul Lavoie, who many of you are familiar with. Kirti Patel is the new CMO. He joins DECD after 10 years leading Eppendorf Manufacturing, a manufacturer of laboratory instruments for the life sciences industry. So we're excited to have him. He's excited to be part of DECD and help continue to move the important manufacturing sector to the state of Connecticut forward. So thank you very much. Look forward to hearing any of your questions and feedback, and help yourself to some Smarties that are complements of Constep.
Thank you, Nancy. Much appreciate your words. At this point, I'd love to ask our CCAT's Executive Director, Andrew Bond, to come up and give us a few words.
Thanks, Nasir. I won't take long. I'd just like to welcome all of you here to the Advanced Technologies Center on behalf of the whole CCAT team. Right, we're really excited to have you here this afternoon, and look forward to a great presentation. Just really want to echo what Nancy said. From a CCAT perspective, we're here for you, right? Regardless of where you are on your journey, right? We can help figure out where you are and work with you to figure out where you want to be. There are many businesses like your own that don't even know where to begin, and that's okay, right? Because we've done this with a lot of different companies, right? And so we can help you find that right entry point, whether it's taking an awareness course, right, on model-based definition, so that you understand the requirements that are coming, or to work with you on, hey, I know I want to go into additive, but I don't really know the software or the implementation that I want, right? So we can work with you up to and including, right, as the signs say, right, working with you on the stimulus capital that we also administer on behalf of the state of Connecticut, right? So think of us as your one-stop shopping partner, all right, on that journey, right? And as Nancy said, it starts with what just being here today and seeing the technology demonstration, talking to the staff, right? And so if there's something that's on your mind, talk to one of us. We've got Julia from our programs team over here, Eileen, and everyone knows Nasir. So with that, I'm going to turn it back over to Nasir for the main event. Great, thanks everyone.
Thanks, Andrew. So the topic of today's presentation, as I mentioned before, very exciting technology. I'm sure most of you are aware of this technology, autonomous mobile robots, or AMR. You may have heard them referred to as AGVs, and perhaps some other acronyms. But we're going to give you a brief overview of what AMRs are, in case it's not common knowledge. And then we're going to go into a deep dive. We're lucky to have Rishabh Agarwal here with us today. He is the president and co-founder of Peer Robotics. And the system that you see here in front of you is one of many of his products. So you'll get a good opportunity to see the different systems that are available, what their capabilities are. But more importantly, after the presentation, we're going to have the opportunity to actually show you. Rishabh will actually show you the interface to the robot, and he'll go through, kind of what's involved in programming it and such. But we'll be here after the main presentation for questions and answers and more in-depth discussions. So I welcome you to stay even after we're completed here. So we've broken up the presentation into these categories here. The most important, that I really want to get across, once you understand basics of what the AMR technology is, and specifically the Peer Robotics solution, what it means when you integrate this into what we call the smart manufacturing, system. So we have one example of that, using inspection as a way to kind of demonstrate, value of using an autonomous mobile robot in conjunction with an inspection system, and what that can actually mean for you and your manufacturing processes. And then we'll go into a little bit of the numbers. What are the benefits of AMRs? What are the energy savings? What are the cost savings, as we compare them against traditional means of moving, material or parts around your shop floor. And then, as I mentioned, Rishabh will show a live demonstration in terms of the interface to the robot, and some details there. So a very brief introduction to autonomous mobile robots. These are intelligent, they have intelligent, autonomous navigation. So AMRs use sensors and machine learning to navigate manufacturing environments independently and adaptively. And you'll learn more about what we mean by adaptively. It has dynamic route adjustment. So unlike fixed path systems, AMRs dynamically adjust routes based on environmental changes for efficiency. It integrates with the Industry 4.0 systems. AMRs integrate seamlessly with smart factory components, enhancing productivity and reducing costs. And AMRs improve operational safety and efficiency by performing tasks without human intervention, right? So that's the main key takeaway here. It's without human intervention, and this is where you'll see a lot of the value. So on a high level, there's a lot of different energy efficiencies you gain by going the route of using autonomous mobile robots for part transport, right? There are other systems that are out there, and we'll go through some of them. AMRs consume up to 10 times less energy than traditional forklifts, right, due to advanced design and technology. AMRs use intelligent power management, including low power idle modes and opportunity charging to save energy. And it's reduced energy consumption by AMRs, supports sustainable manufacturing, and helps meet green energy goals. If we compare it now to, traditional forklifts, there are limitations with forklifts. I mean, manual operation causes higher accident rates and inefficient workflows due to inconsistent route and idle time. AMRs provide autonomous navigation, real-time task scheduling, and improved operational efficiency in manufacturing. AMRs reduce labor costs and enhance workplace safety by minimizing human error and accidents. And AMRs enable just-in-time delivery and waste minimization, adapting to changing environments in smart factories. To get into more specifics about each one of those points, I'd like to ask Rishabh to come up and talk more about his AMR technology.
Thank you, Nasir. I hope everyone can hear me. Awesome. So I think Nasir covered one of the very important aspects of what are the benefits of AMRs, why you should consider using these technologies in your shop floors or manufacturing line, right? The most important thing is that automation, right? Like we first of all want to make sure that these robots can provide on-time and reliable delivery of components. One of the majority cases when we talk to customers on why they are looking to automate some of their part movement, it's on-time delivery. It's making sure that there's no error introduced during this process. Mostly technologies like forklifts or pallet jacks, including kind of like the manual workflow, always had these once in a while incidences where forklift in particular is a safety hazard in some of the regions, but even with manual intervention in other areas with pallet jacks, users would always have to rely on communication, and if there's a break, the line is down. So that's a big problem why users are constantly looking at automating their material workflow. Now, on a very high level overview, what we do at Peer Robotics, we can summarize that we help automate movement of trolleys, bins, and pallets. It's as simple as that. So if in a factory floor or a warehouse, people are moving trolleys or bins or pallets, Peer Robotics can help them automate that entire process by making sure it's adaptable to the user requirements or to the workflows. So we have different platforms. You're seeing one of our earliest platform, which is RM250. It's a 250 kilogram or 500-pound payload capacity system, very much designed to transfer bins. So some of the key customers we have with this particular technology are Samsung, Suzuki, some of the other smaller scale industries as well, like BioWorld, where what they're doing is doing bin transfer at a time. So they have these bins, which could be electronic system, could be another mechanical system that needs to feed to a production line. And mostly those feeding were either previously going through conveyor systems, which were very rigid. So if they had to change anything in their workflow, add additional stations for quality check or different evaluations, they were very much restrained by someone coming in, taking it from the conveyor to outside, and then taking it to the inspection line. So even companies like ABB, Whirlpool, like they had this big struggle where a component had to be taken out for random quality inspection and then brought back in. And this was very difficult if it was all on conveyor system. So a lot of our customers use this type of platform structure to transfer bins or single item at a time across their manufacturing line. We have a similar version, which is a little bit bigger, that mostly customer use for, again, bins is one example, but even heavier trolleys. So the robot can go underneath the trolley, lift the entire structure, and bring it back for dropping that trolley at that designated location. So customers are really using these platforms for primarily bin movement and some form of trolley movement. Then we have our new series platform, which is Peer 3000, which we went through the redesign and understanding, okay, what are the other things that customers are doing and how can we make it more efficient so that customers or small and medium scale enterprises in particular won't have to invest significant cost on adopting these technologies. And that's a major barrier because a lot of technologies are already, or customers are already doing operations unique to their own requirements, right? So they would be using a certain type of trolley which fits their certain type of material, or they would be using a workflow of going from point A to point B to point C, which is again adapted to their requirements. And that's where we designed a platform which could be personalized to user's trolley. So very much like how a person goes and grabs the trolley by the handle, and I'll show you one of the videos. The robot can go grab the trolley by the handle, and we can create these custom coupling mechanisms for the existing trolleys and move it autonomously. But the same robot can also do pallets, whether it's American, European, and completely built upon Vision Stack to even provide values like digital twin and data back to our users. So essentially, the core reason why Peer Robotics exists is that we can enable these robots to learn from humans in real time. What it means is anyone on the shop floor can grab these robots, move it around, and in this process, the robot is recording data from its cameras and LiDAR systems and learning how to do the operation based on user feedback. So at any point in time, the user can teach the robot on how this robot should function, what path it should follow. It's autonomous, but user can guide the robot that while you have 4 different ways of doing this particular task, I prefer you doing it this way because that's more optimal for my use case. And that at any point in time, user can take over the robot to be in semi-autonomous mode. And again, I'll go through some of these videos where robot can be switched to a follow me mode, where let's say a user is doing a task and they want the robot to follow the person. So they go to a location X, the user takes over the robot is just following the person. They might pick up something, drop something on the pallet or on the robot, and once they're done, switch it back to autonomous mode. And then finally, as Nasir was also mentioning, one of the core things is that all the data that robot collects gets passed on back to the users. So it's not just about automating the physical layer, but it's also about the digital data that we can provide back to the users to help them go towards this era of Industry 4.0 or even beyond, right? So whether it's the digital twin that we create as we are mapping out the facility, or even controlling directly from the MES or WMS system that which pallets we have moved, where we have staged, what is the stage of one particular pallet in different location. All this data is given back to the user so that they have the real-time access to that data. So just to go a little bit more into detail, this is the RM series platform. As I mentioned, they're very compact in size. The idea is to make sure that these robots can go in and deploy into compact production line, transfer bins, and really offer a flexible solution. So the product is designed with camera systems, safety LiDAR systems, and after the kind of talk, we will go into more on the hardware side, but it can go charge itself autonomously. Anyone on the user side can even swap out the battery pack. So if they want 24/7 operations without any breaks, they can also do that. But then more importantly, we can create a custom attachment. So the conveyor top or different layer systems can be created based on the user requirement, which is personalized to their operations. Same thing for RM500. It's essentially just a higher payload capacity system and really used for lifting solutions or even like heavier items, whether it could be an engine part or some other custom rigs that we want to create on the platform. It should work. Yep. And this is just one example. We'll go on to the same interface and I'll show you guys these things again. But the whole idea is that anyone on the shop floor can train the robot in real time. So they can switch the robot to a learning mode. And as soon as the robot goes into the learning mode, as they're moving it around, the robot creates a map of the facility. So you can teach an entire space to the robot by just walking the robot around like a trolley. And you can even teach a specific path. So you can tell the robot that, okay, now I'm going to teach you a specific path you need to follow. So you don't go into any open space, just on this taught path. You can easily teach that using the same interface. And that's the real patented value that we bring on table, where we allow people on the shop floor to integrate, deploy these robots, to have that level of control. Because everywhere else, you would have to rely on complex engineering to come and reprogram these systems. And as we know, small manufacturers constantly change their operation. And if something changed tomorrow, we want them to have the flexibility of reprogramming or adapting this technology. I'll start with the video for Peer.
In today's industrial space, automation is essential, but scaling it today means scaling complexity.
That we saw is that whenever
high
the
costs,
users
rigid
were trying
workflows,
to
and endless training.
AMRs or other technologies,
Adopting the
they were
automation
very
should
much
not be
limited
this
by
hard.
their existing infrastructure. Hey, I have a certain type of
That's why we
problem
built
I
Peer
can't-
3000.
I have a
Built
certain
to work with
operation
your
I
existing
can't change that.
infrastructure, your workflows,
That's why
and
we
your
designed
assets.
this platform
It's
from a
adaptable,
complete
intelligent, and
ground-up
collaborative.
perspective of how it could be adapted.
With its adaptive nature,
the
Peer
robot is
3000
integrated
can
with 6
recognize and
cameras, 12
differentiate
in
between
total, but
trolleys,
6
racks, and
repairs.
pallets.
And in real time, it's
And with custom
understanding
attachment
what it's
modules,
looking at.
it
Is
allows
a
to
pallet?
adapt to
Is
your
it a
existing
human? Is it a
assets,
wall? Is it a
automating them
pillar?
without
And it
modification.
knows kind of
No need to
what
change
particular
layouts,
object
replace
is-
cards, or
I'll just
upgrade your
stop.
infrastructure
So,
and pallets.
like,
And differentiate between trolleys.
So as you might notice that as the robot is moving around, it's clearly detecting that, okay, that's an American pallet, that's a trolley, that's a person that I'm trying to track at. So when it's navigating around, it has different behaviors for different assets. Because let's imagine the robot has to go and drop a pallet. It knows that pallet to pallet staging would happen, right? So if there is another pallet very close by, I still want to go and almost probably just like 2-3 inches close to that pallet and drop that pallet. We don't want space unoptimized or unutilized. Whereas if there is a person, I don't want to go 2-3 inches close to a person and drop a pallet there. So that's where it's very important that the entire robot is built upon vision intelligence. It has LiDARs for safety, but then entire
It's
intelligence
racks and
is built upon
pallets.
vision stack to enable that use.
And with custom
The other core aspect of the platform is we wanted to create a system that adapts to our users' requirement rather than asking our users to change their operations to adapt to the robot's requirement. And that's where the hardware is designed from the point of view of creating end effectors. We are very much aware about manipulators having these different grippers or different end effectors for different tasks. We brought in a similar concept where we are saying that, hey, let's swap out these different attachments to adapt closer to the user requirement.
attachment
So what that
modules,
means
it allows
is
to
that we
adapt to your
can
existing
create
assets,
personalized
automating them without
solutions for our
modification.
customers.
No need to
Whether
change
they are
layouts,
moving a
replace
train of
cards, or upgrade
trolleys,
your
whether they are
infrastructure.
moving a closed American
just
pallet,
works.
European pallet, the robot can adapt to those requirements.
Peer 3000 learns by
Everything
observing
is
its
happening on
environment.
the edge.
And with its
So there
extensive
is
sensor
nothing
suite,
going
it captures
outside.
rich
The
visuals
entire
and spatial
processing on
data.
the intelligence
This
side,
enables the
safety
robot
side,
to build a
is
human-like
happening on
understanding
the
of your
robot
floor layout,
inside the robot.
allowing it
The
to
only
navigate
time we
naturally and
communicate to
safely
the
within your
cloud is
dynamic
to pass
environment.
on the information regarding which mission we are going to do
And because all
next,
learning happens
or
on
to
device,
take that
you
feedback,
get
what
real-time
we have
performance
completed and give
with
back
no
to the,
reliance on cloud or
MES
added
system.
IT system.
But there is fundamentally no reliance on the cloud.
Peer 3000 is
infrastructure
collaborative by
because we wanted to
design.
build the system
Operators
that
can grab and guide like a regular
adapt and
pallet
learn
jack.
and can be realistically performing. We all know Wi-Fi in manufacturing is not the best one, right? So we don't want to rely on any safety or intelligence aspect, which is Wi-Fi dependent. But then similar to RM250, the
Collaborative by
robot
design.
can also understand
Operators
human
can grab
feedback.
and
So you
guide
can
like a
grab
regular
the
pallet
platform,
jack.
move it around,
Or use the follow me
acts
feature
just like
for
a pallet
intuitive
jack.
and hands-free
You can
collaboration.
take over the system at any point in time, or tell the robot to follow a person.
From narrow aisles
So the
to varied
robot can become
payloads, Peer
collaborative,
3000
follow a
flexes to
person,
your
and I'll
operations
show you
reality.
more videos like
Peer
we can have
3000
the
is more than a
open
robot.
discussion after
It's a
the
smarter and simpler way to
where I
automate,
can walk you
scale, and
through
work.
how this
It's the
platform
robot
work
that
and
works for you.
that and what areas we have already deployed these systems into. But that's a very high level overview of the platforms that Peer Robotics offer. And our whole mission is that we want to build up something which can adapt to our user requirements, and we want to empower people on the floor to have the control to deploy, train, or reprogram these robots as and when they want. So with that, I'll bring back Nasir. He will talk more about how the joint end-to-end integration can happen with these platforms, with AMRs to other MES or manufacturing related ecosystem.
Thank you, Rishabh. So to point out, you saw that wonderful presentation of the technology, all the capabilities that are built in. Essentially, that just means that it's easy to use, right, for people. on your shop floor. You turn it on, you get it into a certain mode, teach mode, and you do everything that you would do normally, right? There's no extra. The learning curve is almost nothing. And you know, the way the technology functions after you teach it is completely autonomous, and it's aware of its surroundings. And you can, you know, just from the technology standpoint, you can really grasp the value that a system like this would bring to a manufacturing shop floor. And what I'm going to attempt to do now is to give you more information as it comes to, you know, integrating this into a smart manufacturing system. And then I'll go into one example use case that we're setting up here. Actually, we're setting up multiple use cases, but one specific use case for autonomous inspection. But as it relates to smart manufacturing, AMRs play really a pivotal role, right, in smart manufacturing by enabling, like Rishabh discussed, real-time data exchange, adaptive automation, and seamless integration with digital systems. They can connect to different IoT devices, manufacturing execution systems, and enterprise resource planning systems, as Rishabh pointed out. AMRs also support lean production by delivering materials just in time, and that's very important because there's other systems that just don't do that. And they really reduce your inventory overhead. Their ability to dynamically reroute and reschedule tasks obviously enhances responsiveness to production changes. And Peer Robotics AMR, specifically with their intuitive dashboards and collaborative features, really exemplifies, you know, how smart robots can empower human workers and streamline, you know, your operations. This integration can really lead to improved productivity, reduced downtime, and greater scalability in manufacturing environments. One of the biggest benefits that we saw with the peer system was really how easy, as I mentioned before, how easy it was to set it up. We have experience with some other brands out there. Everyone has a pro and a con, but to highlight, you know, Peer Robotics system, it was a matter of getting it on our shop floor, and as Rishabh pointed out, putting it into teach mode and literally just pushing it around, and it mapped your floor, and then you can give it missions. You'll hear more about that later, but that was just the experience of what it means to set up an AMR, to actually get it on site and to get it, if you will, programmed to complete certain tasks, is very is simplified. So what I'd like to get into now is to talk more specifically about the use case, you know, one of the use cases that we're setting the system up for now. But before getting into that, I want to talk about non-contact inspection in case you're not familiar with it or it's not common knowledge. Typically with inspection, we talk about manual inspection, um, um, you know, maybe using contact-based systems like CMMs or hand measuring devices such as, you know, calipers and other measuring devices. So just to level set, let's quickly talk about non-contact inspection and what it is, and then how that relates to, you know, the AMR system that we're talking about here today. So the main features of non-contact inspection, obviously with any inspection system, there's calibration. You have to calibrate the unit. It is a vision-based system. You'll see more about that here in a minute. But the interface you're seeing up on the screen, the camera live view is on the right. And what the system does is it uses vision to reconstruct a 3D digital replica of the physical part, which you see in the center of that interface there, that yellow model. And it's you know, different systems have different accuracies, but you can then use this digital, you know, virtualized version of your physical part to then extract measurements off of. So in the scanning software, you set up a project, right? You set up the, you know, the instructions of how to scan the part, all the parameters that go into scanning, then post-processing. So once you have multiple scans, you want to align all the scans together, and then go through a process called merging, or some other systems call it, I'm losing a word here. like a full 3D reconstruction of the mesh, basically. Then after that, you put that mesh into, you export that out and you put it into an analysis software, or you do it within the scanner software if the particular brand has that built in, and you extract measurements off of it. So as an example, this is a deviation analysis that can be done within most scanning solutions. And here, what we're doing is we're just importing the CAD model. And then we're using the alignment tools within the scanner software to align the 3D scan to the CAD. We can do that just on best or with specific features. So we have to do, if we have datums that we have to align to, we can use that in the software. And then the first thing that we can run is a deviation analysis. And what this is for every point that's captured with the 3D scanner, it can calculate how far off it is from the CAD surface, and it colorizes that. So what you're seeing here in green is a range that was set to say that if it's, colorize all the data points that are within plus or minus, let's say 5,000s, which might be a global tolerance on the part, to colorize it green so we can see what's intolerance, and anything that's out, color it other color. So in this case, red is where my physical part has too much material, and blue is where my physical part has not enough material. So you can see exactly where it's in and out. But then you can also extract hard dimensions off of this as well. So there's a lot of, like I mentioned, there's a lot of different units that are out there. There's high accuracy systems, there's flexible systems, compact systems, multi-sensor units as well. These are just some examples of units that have, full robotic automation. When we walk around the lab here on the other side, I have a little demo set up of a scanning unit just to show you a little bit more about what the systems do. But as I mentioned, you can do full extraction of dimensions, generate first article inspection reports. You can use it for other applications as well, like reverse modeling, where if you have a component that doesn't have a CAD model, or the drawings difficult to read, or maybe you don't have a drawing on it, and you want to create a CAD model for it and a drawing. So you can scan it, you can model it from the scan, and then you can capture, that the digital data on the physical part. Other applications would involve, like if you were to manually modify a part, for example, for fitting it into an assembly, and you want to capture that change, you can also scan the part and add that change based off of the scan data set. So this is just a quick video about the process. Normally you would put a part in front of the scanner, and you can see the robot. The scanner is attached to the robot, so the robot's just moving the scanner around. It's working in conjunction with a rotary system, so that we don't have to move the robot quite as much. We can just present different, views of the part using the rotary, and then we can move the scanner to get top, middle, and bottom of the part there. But what it does is it projects a series of line patterns, and it just uses the camera to then reconstruct the full 3D model here that you see on the screen. But this is in mesh format. So really the data here is a bunch of 3D points along with the triangles and normals and other information that mesh data contains. But typically with these systems, you can get millions of data points, right? With the system that we use there, it's a 3-megapixel camera. They go up to 45. For each shot, you get 3 million points. So if you add up the number of shots, you end up with a lot of data there. This next video is going to show what happens once that data is captured. We import the CAD, and in this case, we're using model-based definition, which is CAD with the embedded PMI. So that is all the callouts of what needs to be inspected. So we don't have to set that up necessarily manually. It just gets imported. And then what we can do is generate the first article inspection report by just clicking a button, and then just importing that scan data set that we had grabbed, and then letting the inspection software extract all the measured data based off of the callouts that are already there. So basically, this is a file import, and then the scanner software, once it finishes scanning, it'll import that scan data set as long as you set the pointer up in the software. And then you'll see it go through the alignment and then extraction of all the data, and then just generate the report. And you can export that out in different formats, like an AS9102 or a PPAP report or other formats. So that's just a general high-level overview of non-contact inspection and the process there, just a level set. And what I just talked about is a process where a part is produced and then we inspect it, right? So the problem with that is that we're not going to know if a part is made correctly until after the fact. So we would have gone through the whole manufacturing process to then scan it or to inspect it, only to discover that the part doesn't meet specs, right? Unless you're doing in-process inspection, maybe hand measurements, or maybe some kind of a CMM system that you bring the parts to, or maybe a vision system that you use to kind of scan parts in between. But the final inspection is typically where the part is accepted or rejected. And if we waste all that energy that goes into getting that part up to that condition, where now we're at the point of scanning it to discover that it doesn't meet spec, we've essentially wasted that energy. So if we look at how can we take advantage of inspection systems and bring it to the machine, so that we're not just doing in-process inspection where we're going from one machine to another and we inspect it in between, but we're actually doing inspection on the machine, and we're using the scanner as a sensor to communicate back to the system the corrective action that's needed to get that part in spec. Okay, so this is an example video of using one of the smaller compact units and actually integrating it with a CNC machine. And you can very quickly see the value of that as we go through the video. So in this case, it's a CNC machine, and we have a part. This is just the final part of the machining operation. Is cutting those two slots that you see it's machining currently. And what happens is that once the machining operation is done, the machine actually goes and picks up the scanner in the spindle, and we scan that part. Now that part can be scanned at any point. So if we do one operation, we can scan it after that, do another operation, scan it after that. But in this case, what we're picking up is that the width of that slot that it cut is not in spec. And because the scanner is integrated with the machine, it knows what tool cut that slot, and it sees that it has no radius offset. So because it knows the deviation of the slot, it can actually provide information back to the machine to say, okay, do a tool radius offset to compensate for the tool wear that's causing that slot to not come in spec, and now go back and remachine that specific tool path, that specific operation. And you just saw there that it went and did a very, very slight trim cut. And the scanner will then go back and rescan it, and it'll check to see if that slot is made now is if it's within tolerance. And in this case, you can see that it only required that one iteration to get the width of that slot to within two 10,000ths of an inch. The system can go through, we had it set up to go through 3 times. So if it did it once and it made that corrective action, scanned it, and if it wasn't in spec, it would do it again. After the 3rd time, it would just give the operator the notification that the tool needs to change. It can't do anything more to correct. In this case, it's a tool radius offset, so it's pretty straightforward. But in other cases, there might be other corrective actions that's needed, like tool length offset, maybe feeds and speeds override, things of that nature. But you can see here right away that while my part is still on the machine, I'm not wasting any time. I'm not taking the part off the machine, putting it into another operation, and then scanning it after the fact or inspecting it after the fact to understand that the part's not good anymore. In essence, this becomes an autonomous inspection, if you will, where the scanner communicates directly with the machine, and it extracts dimensions, and based off of those dimensions, knowing the tool, the actual operation that's associated with the particular feature, it can re-execute a machining program with adjusted parameters on the machine, thereby giving the machine the ability to kind of sense what's happening and make a corrective action. If we look at it from an integration standpoint, that means that different machines have different environments. The CNC machines have coolant. It's a pretty caustic environment. You need to have a protection, around the scanner. It is a vision-based sensor. It has lenses. And so if you think about, what I just showed you there, we're saving time, and we're making those corrections at the machine at the time that it's needed. But the issue is on integration and about modifying the machine in order to get the sensor in there. different machines, like I mentioned, have different environments. Well, what if we can bring the scanner to the machine? And what if the machine can actually ask the scanner to come over, scan the part, and then another machine can then request, for that same scanner to scan the part on another process. This is where the integration with the autonomous mobile robot can be extremely beneficial, because as you heard Rishabh, and even demonstrate through the videos, is that this system is so simple to program. You give it a mission, you tell it where you want it to go and what it needs to do at that location. So in this instance, where you see the autonomous mobile robot here at the bottom, we have a cabinet system built on top of it that holds a collaborative robot, and then the collaborative robot has a scanner attached to it. Now, of course, this is on a tool changer, so we can change the end effector. There's several end effectors here. There's a pinch gripper, vacuum gripper, vision system. The scanner is just one end effector on there. But we're in a circumstance here where we have a completely mobile unit that can be programmed to do on-machine inspection and provide that feedback to the machine controller or to an edge device connected to the machine to do that corrective action at the point when it's needed, right? Thereby saving time, saving energy, and saving you from having to reject parts. The goal here is to have 100% yield. So here's an example of the application where the AMR actually brings the whole scanning unit over to the CNC machine. The CNC machine would request the AMR to come over, and the collaborative robot would then activate, perform its task as the AMR brought it to the location, and it would go inside the machine. It would scan the part, come back out, provide that data through the MES system. So the CNC machine can actually pick that up and adjust whatever parameters are necessary based off of the root cause analysis and the parameters that we have mapped to what caused the issue, and then go ahead and perform that corrective action. So again, here we're avoiding the circumstance of having to specifically integrate it into a machine, and then to subject the scanner itself into a caustic environment. Here, the AMR is bringing it to the machine, and now it's that system can be used across the shop floor wherever it's needed. This is just a quick flow diagram of the process working, right? Using model-based definition. There's several different formats that can be used here. Native CAD files like CATIA, SOLIDWORKS, NX Creo, or a neutral format called QIF, Quality Information Framework. That is a CAD model with all the embedded PMI. If you're able to utilize that format, programming the system is easy. You just do a file import, right? Everything else is taken care of by the software, the programming, the robot motions, the actual first article inspection report generation, extraction of dimensions. It's literally a few mouse clicks. And then with what you saw demonstrated with the Peer Robotics system, it's very simple to program. You push it around, you give it a mission, and you're good to go. We can even take this a step further and say, well, how do we then, we're taking advantage of an AMR system to do, stop the manufacturing process at some point, take a scan of the part, understand where we're at, provide corrective action control. But what if we can then even save time on the machine? Because what I'm just presenting here right now is that the process does have to stop, and the scanner does have to go into the machine and scan the part. So that is adding to your overall manufacturing process. Well, what if we can train what's called a predictive model? So let's say that we're doing a batch of 100 parts, and the AMR system is used to scan the parts, intermittently as it's being produced on the machine, while we're collecting real-time data off the machine, either using an edge device or sensors connected to, a main platform where that data is being streamed. And we take the real-time data and we take the inspection data and we use machine learning or standard algorithms, statistical algorithms, to train a predictive model. So we know that if certain parameters on the machine, certain signals are going in a direction, that the dimension of this feature is going to be out by this much. Now we can actually do real-time control, real-time corrective action control based off of prediction data. So what you're actually seeing there on the right is a prediction of the deviation of the part that would be currently being produced on the machine. Where the AMR comes in obviously here is that you can set this up. You can set it up where you set up the missions to go and scan parts on the machine to collect all this data. As Rishabh said, we have even more data coming off of the AMR that we can leverage in this particular circumstance. So that was a very specific use case, and what we're setting up here. We will have that actively working towards the beginning of next year for demonstration purposes. We will hold another one of these Connecticut Smart events to demonstrate that process next year if we have the opportunity. And so if you want to see that working and all the integration work that we're doing, we'd be happy to present that. But stay tuned for the end. We are looking, as Nancy mentioned, to do company-specific projects. So there's some other opportunity to get some hands-on with this. Now I'd like to kind of switch over to giving you the numbers, right? Quantitative benefits of AMRs in manufacturing. So we got a kind of an overview of AMRs, a specific use case that we're setting up here at CCAT for autonomous inspection. It's also for part transport between machines. But what does it mean in terms of numbers? What is it saving you? Is it actually energy efficient? So if we do a comparative, cost analysis of AMRs versus traditional systems, AMRs offer a substantial cost savings when compared to traditional materials transport systems in manufacturing environments. For instance, the operating cost of an AMR is estimated at $40,000 to $50,000 per year, whereas a forklift combined with driver incurs costs ranging from $200,000 to $280,000 annually. Right? This translates to an approximate 80% reduction in operating expenses if you switch from traditional to AMR means of transport. Additionally, AMRs operate at just 15% of the cost of manual cart movers, making them a highly economical alternative to human labor for material transport when compared to traditional conveyor systems. And AMRs can deliver a 50% cost reduction for equivalent work, especially when conveyors are suboptimally loaded or used kind of sporadically. These figures underscore really the financial advantages of deploying AMRs, particularly in large-scale operations where labor and equipment costs really are the driver. They're very significant. The cost efficiency of AMRs is further amplified by their ability to operate continuously without breaks, reducing need for multiple shifts and associated labor costs. So when it comes to energy savings, we saw a lot of the time savings and other efficiencies that it brings, but AMRs are significantly more energy efficient than traditional material transport systems. We talked about forklifts, we talked about conveyors, but studies have shown that AMRs consume, like we mentioned before, 80% less energy than these conventional systems. This reduction in energy usage not only lowers operational costs, but also contributes to a reduced carbon footprint, aligning with sustainability goals in modern manufacturing. You can see that you can have a optimized routing and smart battery management help AMRs minimize energy consumption and then the environmental impact, as we just mentioned there. But the takeaway here on this slide is that it consumes up to 80%, right? It's not 10 or 20%, it's 80% less energy compared to forklifts. And as we saw on conveyors, it's more energy efficient there as well. So kind of to summarize, AMRs improve order fulfillment speeds by 20 to 30%. AMRs enable 2 to 3 times increase in productivity. AMRs navigate very complex environments. So imagine setting up a conveyor system in a complex environment. AMRs can do that with ease. AMRs operate, continuously without taking breaks, and that ends up in accelerating throughput. There's some other byproducts here as well. So AMRs do, they automate the heavy lifting, as we saw with the 3000 series, lifting, and repeatedly lifting heavy payloads, reducing workplace injuries up to 70%. They also lower physical exertion and exposure to hazards. And AMRs safely navigate tight spaces near human workers. So the ROI and the takeaway here is that most AMR deployments achieve payback within 12 to 24 months. Okay, AMRs offer cost savings of 80% over forklifts and 50% over conveyors. And AMRs offer you the ability to design facilities that are more compact, right? Not having to design in conveyor systems or making ways for larger forklifts to transport parts. So you can see here the benefit, a lot of different ways of seeing the benefits of autonomous mobile robots. Like I said, we are setting up a specific use case, but I'll walk you through the digital side of the Advanced Technology Center to show you the setup of our autonomous manufacturing cell. We have multiple different machines in this cell, anywhere from CNC machining to laser machining centers to sheet metal benders to laser welders, assembly stations, and cleaning and painting stations. And we want to be able to demonstrate the true value of using a system like this without having to design traditional part movement, part transport using conveyors or forklifts. The whole purpose of the autonomous manufacturing cell is an environment for you to see the value of these different technologies. So if you wanted to see or try out a specific use case, you have a part, you want to run it through some of our machines, and we can use the AMR to show the value of, how its, purpose can really help streamline your processes. That's what we're here for. That's what we can demonstrate to you. Like Nancy mentioned, we do have the Connecticut SMARTE program. Putting the QR code up here again, so you can take a picture of that. That'll bring you to the sign-up page. There's several different offerings through the Connecticut SMARTE program, one of which is smart manufacturing technology demonstrations. That's what we do here at CCAT. You'll have a menu list of things that you can select. You can select multiple. If you do want to do a demonstration project, do select the Smart Manufacturing Demonstration Project checkbox, and that'll put you in line so that we can engage with you and come up with a scope of work, and then we can do the demonstration project for you. These are some other projects that we can do. Nancy mentioned these at the beginning, just reiterating that, and really putting the value up here of some of the other projects that we can do on the Connecticut SMARTE program. So with digital thread, really our aim is to show you how you can save 50 to 90% of CNC programming time. For digital twin, we want to show you how you can save 10 to 30% off your CNC cycle time. For autonomous part transport, we want to show you how it lowers costs and saves time in transporting material. With autonomous deburring, we want to be able to show you how the system can be automatically programmed for your deburring operations. AI vision leverages deep learning to perform visual inspection. We can teach the camera what to look for. So it's not traditional programming for machine vision. It's AI-based vision, much easier to use. And that will be one of the sensors that we're going to build into this system here, so it can actually go over to machines and do that visual inspection. Do I have a nick? Do I have a scratch? At the assembly station, what's missing? Do I have a missing bolt? Do I have, are all the components here? Is my part within the work holding, or is it slightly skewed? Those kinds of things we can do with the vision system attached to the AMR system that we're going to have demonstrated here. And then autonomous inspections or automated inspection here. In this case, we can show you how to leverage non-contact inspection and model-based definition to automatically generate first software inspection reports and to generate, non-contact inspection programs that use robotics for scanning. We do have the first 2 event recordings that you have access to. So if you'd like to learn more specifically about what digital thread can do for you and what digital twin can do for you as a manufacturer, these 2 QR codes will bring you to the videos that you can see. We actually did use cases, so you'll see the time savings and the cost savings. To take away from this slide, the digital thread enables automation of production programming, and the digital twin can help control manufacturing variability. Both of those we're going to incorporate onto the AMR system. So this is a very powerful platform to enable a lot of different processes to happen. We also have grants that are available. So if we do go through a technology demonstration with you, and you do see the value of the technology and you get to the point of wanting to adopt the technology, right? You can get the quotes, and then we'll work with you to bring you to the right grants that you can use to actually onboard the technology. All these grants that you see up here are one-to-one cost share for the most part when it comes to the IVP and the MVP up there. The IVP, I'll talk more specifically about those 2. But generally speaking, it's a very, very easy process. It's an online form. You submit a couple of bits of information. As long as you're a Connecticut-based company, you're between 1 in 300 employees for one of the grants and 1 in 100 employees for the other grant. You can very easily get half off the technology, up to the max that grant pays. So this is a great opportunity to get funding within a week. We're typically only a week or 2 weeks, in terms of responding back. And this is prior to purchase order. So you would submit the quotes, and you get an application number. And if within a week or 2, if you're approved, you'll get a check cut for half the amount of the technology up to the max of and then you can proceed forward with purchasing. So it's you get the funding prior to purchasing. This is the QR code to the grants page if you want to take an image of that. Like I said, the most applicable grants here for the technologies that we're talking about are the manufacturer voucher program and the innovation voucher program. So the manufacturer voucher program gets you up to $100,000. The innovation voucher program gets you up to $25,000. Both of those are one-to-one cost share. As an example, if you were to get a quote for a system that's $100,000, if it's a piece of machinery, if it's a autonomous mobile robot, if it's a collaborative robot, you'd want to go with the MVP. That'll get you 50% off. So you'll only be paying $50,000 out of pocket. If it's a if it exceeds 200,000, you're capped off at 100,000 for the MVP. The IVP will get you up to 25. So if you have a quote for for $50,000 for a technology, you can get $25,000 paid for that. There's also additive voucher program, cybersecurity adoption program as well. But do visit our grants page. These are all through the grants or money that's available through the state of Connecticut that CCAT administers. Take advantage. You can use all of them at the same time. It's not one or the other. But that's there to help you with offsetting the cost of adoption. With that, I'd like to welcome up back up here with me Rishabh, so we can go through any questions that you may have on anything that you heard today. Also, Nancy is here and Chris from Constep is here. If you want to ask questions about the program specifically, please feel free.
How do the AMRs, when replacing forklifts, manage high racking systems?
That's a very good example. So there are not specific to, let's say, staying at Peer, but there are other solutions as well that focus on racking, specifically racking. So how you can lift the MR to a certain height and feed it there. Then there are some other specific system for managing racking, like ASRS systems, which are similar to AMR, but constrained in that racking solution itself. So the goal is that you bring those pallets or systems into those feeding of ASRS, and then they take care of taking it into different heights and different depths. So looking at these integration with other solutions in the manufacturing, AMRs are typically useful to automate the flow, but they would almost always have to integrate with the existing manufacturing ecosystem. So Nasir gave an example on CNC, right? So how do we integrate with CNC? We could add a manipulator on top of it, and they could enable the AMRs to even pick apart, drop apart, or feed apart to a CNC machine. Similarly, for pallets, what we have done in past as well, where the robot goes and feeds a pallet into an ASRS system, which then takes care of the racking, or the SRS brings a filled one, it takes care of the dispatch. So yes, it's always going to be multiple systems coming together to provide kind of like end to end. But what we have seen for a lot of customers is to start from most value addition step. So a lot of times we have some customers, and one of them is down in Texas, and one of the key things for them is that they have these vertical stackers, which they have been using for quite a long time. But the biggest problem was that when they had to take these stackers outside their storage and to bring certain parts from the production line, that's a safety risk, because at that particular instance, there are people walking in that area, and that's a constraint. So what they implemented is that the robot brings the pallet into a feeding. The stacker still stays, like the person is still doing the stacking, but they never leave the warehouse or that storage unit. So what it does is that, first of all, their throughput is higher because they don't have to go outside. The safety is managed, and the majority of the time that wasted during the movement is now no longer on the human end. So that optimizes the entire cost and throughput for the users.
What industry 4.0 protocols do you support for getting data out of the AMR?
Yeah, very, very important point. And there are several protocols. Like, one of the things I would highlight is OPC UA is a very big standard. So whether it comes to PLC communication or even over the cloud, we do support OPC UA. We do have REST APIs because a lot of the WMS or ERP systems are built upon these API architecture. So the robot directly supports REST APIs as well. But then we integrate with third-party systems. Like, one example is Advantech has these wireless IO modules. So we integrate with those wireless IO, where the robot might be sending API to the wireless IO, but in the end, the communication happens to those secured protocols on the wireless IO. So in terms of, to summarize the communication protocols, all our data goes through a Siemens S7 1200 PLC inside the robot. So as long as a PLC can integrate that data communication, the AMR can integrate that data communication.
Can you use multiple modules to move heavier and larger payloads?
Yes. So we can use multiple modules, but are you trying to say two combining together to lift one? Yeah. Yeah, no, then the platform needs to be different, because let's say if the payload capacity is high, we don't recommend using two to lift that, because again, you're paying double the drive cost and the throughput doesn't come through. So what we have realized is that majority of the cost on these systems you're paying are for sensing and intelligence, right? The payload capacity is not that high of a cost driver. Like, whether it's 500 kilograms or 250 kilograms, the prices are always in the same ballpark. It's a little bit expensive, but not that expensive or not that different in terms of cost. So using multiple robots to do a higher payload or higher size doesn't really make sense, because the output or the ROI drops down significantly for the user. So what we recommend is that If the payload is higher, use the model that kind of adapts to that payload requirement. Size, on the other hand, doesn't really matter that much, because as long as the system is stable by itself, so let's say this robot can take a trolley or a pallet of all the way to 60 cross 60 inches. We have done deployments for some customers where the robot is carrying a trolley which is 60 cross 60 inches. And that's a much bigger trolley than the robot. And you saw one of the photos from Nasir kind of like solutions that we are developing. When it goes underneath, lifts it, or kind of attaches to that structure, as long as the structure is inherently balanced, it doesn't create any challenges for the robot. Its safety is 360. So you can see these kind of like blocks. It covers 360 from that area. So there are diagonal sensors and then cameras in front and back. And the cameras are also designed in such a way that if it knows that that's my body, it would just by default cut that plane. So it can look for just obstacle.
Any other questions? I'll say one of the questions here was about the communication from the AMR. And I can give you a kind of our example, and how we're going to be setting this up. Because we're going to have multiple subcells as part of our autonomous cell. You can imagine that, if we're doing machining a specific part, right? In our example, we have a sheet metal part, we have a base plate, we have camera brackets that we're going to be demonstrating through the cell. The base plate is CNC machined on the CNC machine. And then once it's machined, it has to go over to the deburring, to the robotic deburring subcell where it gets deburred. Then from there, it goes to the cleaning station, and then for final inspection before it goes to the assembly cell. So you can see kind of the progression of starting off from stock to going into CNC, getting machined, then having to be transported to the deburring cell, so on and so forth. But at the same time, we have the housing that's being created. So the housing is sheet metal. It's a 100,000 thick aluminum sheet metal. And it starts off as a 4x4 sheet, goes into the laser machining center or laser cutter. We call it a laser machining center because it's a very high accurate laser cutting process. So it goes into the laser machining and we get the flat pattern cut out. And then it goes from there to the bend cell where the housing actually gets bent up. And then it goes to the laser welding cell where we weld the seams. Then it goes to the robotic deburring cell where we have 3 different heads on the robot. It has a machining head, a deburring head, and a polishing head. So basically, in the process for the housing, we would be machining away a lot of that bulk welded material, and then we would be polishing down or blending in the weld so it looks seamless with the housing. Then it goes from there to cleaning and then over to the assembly station. So that itself has a separate track, right, that it has to go through. So if we have one AMR, how is it going to manage the scheduling of what goes where when? Because everything has a different timing. And so in our case, the way that we're integrating that is through Ops Center. So we've chosen to go with Ops Center as our manufacturing execution system. Ops Center has a module called the Connect MOM, which gives you different connectors. One of them is, as Rishabh mentioned, an OPC UA server. And so what we can do is, and one of the other features of Ops Center, and most MES systems may have this, is an advanced scheduler. And so the Ops Center, our MES system, becomes our main scheduler, right? That is actually controlling the process of the entire autonomous cell, where the communication is between the particular subcell. So for example, the CNC machine, if it doesn't have anything, if it's not detecting that it has anything in its work holding per the sensor, the proximity sensors that might be there, and it knows that it's already finished machining, it has nothing else to do. So it can send a command or a communication via OPC UA from the PLC connected to the Siemens, to the CNC machine controller to Ops Center to request it to schedule the AMR to deliver stock material to the machine. Now, when stock material is delivered, It goes through its machining process. Then it can communicate with the ops center again through OPC-UA to say that it's finished machining, the part is ready for pickup. And ops center advanced scheduler would actually schedule the task in the AMR or the mission for the AMR to pick up the part at its most appropriate time. So the AMR might be doing some other operations at the time, so it wouldn't just go straight in, but it would schedule it in such a way where it's optimal for the flow. So this is when we're talking about optimization of your part transport, and you have one AMR or a fleet of AMRs. We've chosen to use an MES system to do that scheduling and the main communication. So the machines never communicate to the AMR direct. They always go through MES in order to take advantage of that function that MES can bring you.
And I think with some of the other customers, we have seen a very similar infrastructure where they might have already integrated some safety scanners, right? So one good example is that palletizing solution. So a lot of customers might be already doing palletizing of their pallets. Essentially, boxes are being palletized at a location, and they just want the robot to come in once there is no one in that zone. So once it's been validated that there's no human present in that palletizing zone, only then the AMR can enter. So what they have done is they integrated, let's say, a LiDAR system on that station, which is connected to a wireless IO. And if there's any, or if there's any kind of like emptiness that has been reported by the LiDAR, only then it will send out a communication to the AMR that, okay, you can execute this mission now. Before that, it's not going to send over the mission because it knows that someone is present in that location.
So with that, if there's no further questions, this is Rishabh's contact here. You can contact him directly if you'd like to learn more about the Peer Robotics solution. If you'd like to do a smart manufacturing demonstration project, again, use that link to go on Constep's website, submit the form. It's very quick. It's just a few minutes. It only asks a little bit of information. And then you can be put in line. We're looking to get all these projects done before December 14th, I think it is. There's a short time remaining. If we have an opportunity to maybe, talk more about the AMR system either here or, we can come on site and look at your, manufacturing workflow and do kind of a brainstorming session and come up with some kind of solution. We can even do full factory floor simulations, right, with the AMR in there to show you the impact. We can simulate times that it takes at certain machines and really give you numbers that you can use to make a decision on how you want to proceed forward. At this time, I think we're going to go through a live demonstration. We'll connect to Rishabh's computer and he can show you the interface to the AMR. And then once that's done, if there's no further questions for Rishabh, what I'd like to do is to have, maybe, what time is it? 2:32? So what we can do is maybe take about 40 minutes. We'll give it 40 minutes. 3 o'clock. We can schedule a time to just go to the other side. And if you'd like to learn more about the autonomous cell, I can show you some of the equipment that we have. We're in the process of still setting it up. So it's not going to be operating, but you'll be able to see the equipment. And I'd love to be able to show you that. So.
Perfect. So I'll do two things. One is that I'll show this interface first, but I'll go back onto the other system as well to show you how the other Peer 3000 and some of the other solutions that we have done. So one thing you would notice is the kind of like the white gray area that you're seeing right now. This is not for like your production line, but the idea is just a representative so we can walk through it. So typically how it functions is that the open area robot recognizes as white. So whenever there is no obstacle in that area, whether it's from cameras, lidars, what it does is that for simplicity, it showcases that as a white space, that this is my available open space. But when you move around the robot, it kind of creates that entire 2D layout of your factory floor, which is represented in black lines, which are kind of obstacles or main walls, and then the white areas, which are open space where the robot can go. The entire platform you can review from an upside, like essentially what is the battery level of the robot, what is kind of like the different missions if it has right now running on, but you can also assign different missions to the robot. And I'll walk you through first what is actually a mission. But this is the main screen that typically most of the people or most of the operators on the shop floors would have access to. But then we can go into a mission side and we can see what does it mean to kind of have a mission. So let's say I right now take a specific area. Let's say I pick up this map, and then these are tags. Tags in the sense could be locations where you want the robot to go, right? Again, these could be personalized. You can take the robot to a physical location and say record that tag. So you can actually take it there and say that this is your location number 1. But then what you can do is that you can pick up a tag and you can define an action. Now, this is a sample where I can say pick up a trolley, drop a trolley, dock into a conveyor system or into a cell. So the robot can go and dock with an accuracy of plus minus 10 mm. So let's say for solutions where we're doing CNC, and the machine has to pick up an object from there, it's very important that we come under a certain tolerance level. And that's where the robot can take actions like, okay, I'll look for a marker or a feature on that machine to dock myself accurately, or it can just navigate to that location. But for an example, we can create something very simple where we say, hey, location tag 1, go there. And let's say I'll tag 1 again. Once you go there, pick up a trolley, and then let's say go to tag 2, waypoint, and then once again you go there, you drop a trolley. All right. So this is a very simple example on what kind of the robot is going to do once we save this mission is that it will go to that location, pick up a trolley, look for a trolley first of all. Once it finds a trolley, it will pick up that trolley, take it to the location 2 and bring it, drop it. So that's how you can define entire missions on the robot. So now the whole point is that we can create these custom attachments and custom missions, which could be defined by the user. So even if we go back and we say that, hey, apart from trolley, what all we can do, we can even create a custom signal. And I think this comes back to the communication protocol. We have IOs on the robot itself, where we can say that if you go there, trigger an IO from the robot that will give a signal to, let's say, a manipulator on top of the robot that now it's your time to task, or now it's your time to do that task. And then it can also wait. It's a fail safe. So if there is a success, look for pin 2. If there is a failure, let's say look for pin 2 here. And you can define those systems. And even you can say that I expect this mission to be done in 60 seconds. If it doesn't happen in 60 seconds, fail it. So that we have those fail safe where the robot is not stuck into a situation where it's not receiving any signals back to the system. But we can create these custom solutions and we can create these custom missions based on those solutions, and the robot can be adapted. The main thing is that a lot of times people on the floor, they don't have to understand the complex interfaces. So what we do is we have something called simple screen. It's not active right now, but once the robot is integrated and deployed, you would see only these 4 buttons, or you can customize these 3 buttons. So the whole idea is that people on the floor would just have access to these 2 or 3 buttons. So whenever they have to call the robot or send the robot onto a mission, they can just use that. They don't have to worry about any other complexity. Everything is straightforward for them, which is just like a red button or green button that they want to get access to. You can create different users with different rights on the system as well. And this is, again, system-wide across the spectrum. So you can create different users who have access to platforms from different rights. One could be admin, which has everything, but then you can create an operator that can remap or change the missions, or you can create a user which cannot do anything. So you can just say that, hey, no, I don't want mission planning. I don't want logs. I just want like simple screen, right? So I can just say they can just do simple screen, nothing else, or a custom screen if you want to give a custom screen. So you can easily define these roles, and that way users have right access based on the facility requirement. As Nasir was mentioning, you can also go through the complete logging system where you can go in and say that, hey, how much the robot has ran, how much times I had to cancel a mission, how many was the successful, at what exact timestamp we completed it. So this really helped our customers to understand their existing operations, which they were not able to track manually at all. So if we were talking about moving a trolley or moving a pallet from location A to location B, they had no idea what was the exact time it was taking them before, but implementing the robotic systems, they were able to figure out that, okay, this is my choke point. That's where I'm taking a lot of time. So do I have to add subsidiaries around there, like have multiple systems, or even slow down this line because it's not helping me having 4 people here, increasing this throughput of this line, because in the end, my other line is just becoming a bottleneck. So that really kind of allows our customers to figure out how they want to use the platform. Another thing I would highlight is that utilization also depends on what is the active time on the robot. And one of the key parameters that we request our customers and even anyone who is looking into integrating these AMRs to track is that what is the active utilization and success rate of these robots. So that's a parameter that is very important for calculating real throughput of the robot. What that means is, let's say a robot is doing 20 missions in 1 hour. What is the success rate of all of them? There will always be a cancel or failure for any reason. Let's say the robot goes to a location and there is no pallet. So it will come back and say, hey, tried it, can't do it. Let's run that mission again whenever there is a pallet. So those kind of operations really allow us to track how well the robot has been adopted by the customers. And it's not like a single day task. The robot can be integrated and deployed. And now the adoption really matters on, okay, how is the throughput coming out? So what we have seen is typically customers start from all the way 85 to 90% success rate. But very quickly with our platform, within 3 months, we have even seen them achieving like 95, 97% success rate with the platform. So what that means is not that the robot alone is performing, but also the workforce has adapted utilization of the robot. Like they have adapted how they're using it and constantly running those systems. One thing that I'll also highlight, which I think Nasir was also mentioning, but I just wanted to make sure that we cover that part as well, that how the robot can grab and move trolleys. And this is again Peer 3000, one of the series, but you will see an idea that as the robot is moving the trolley, it has a complete control over it. So it's not tugging it, it's moving it literally like a person. So what that means is it can go and stage that part in a CNC machine or in a production line as well. A lot of extrusion machines take out a lot of scrap, which is directly going underneath the machine. And a lot of times the customers or person would come, take a pallet jack, bring that material out or pull the trolley out. With using Peer 3000, our customers have been able to automate even like those controlled movement of trolleys and pallets wherever kind of they really required that particular system. Another thing that Nasir mentioned, and I just wanted to highlight, is the digital twin. So when the robot is moving around, we show on the interface just the black and white line just for the simplicity of usage. But as the robot is moving around, it's creating a complete digital twin of the facility. So it's not just using its LiDAR to map out the facility, but it has this complete 3D data on how the facilities look. So a lot of times our customers have gone through so many iterations that they don't even know what the facilities are actually designed as now. When they integrate these robots and then compare it with their schematics again, they can really understand that, okay, although I initially planned this line to be 1 meter ahead because of certain things, because I'm keeping some storage items which were not supposed to be there, I'm not utilizing that much space. So with this data, in fact, what we have also done with some of our customers is help them optimize their production lines, because they have realized that, okay, previously I was keeping that staging area there, which was blocking my pathway, which I didn't recognize at all was a key part. Whenever I used to go, I won't see that because someone might have moved it. But robot doing 24/7 operation can really say that, okay, at this particular location, I'm seeing these pallets being staged or trolleys being staged, which is not the norm. So it's not just automating the material movement, but it's also giving this data back to the user that can really help them optimize their workflow. And I think one more thing that I'll highlight and showcase is that how the robot can even pick up pallets which are with stretch wrappers. So that's a very unique use case, because once even the pallets are completely covered with stretch wrapper, our vision system really allows the robot to understand that, okay, this is still a pallet, a stretch wrapped pallet, but still a pallet, even if the pathways are blocked in front of the robot. So that's a very quick overview. I'll actually hand it back to Nasir to do the tour. And if anyone wants, I can walk through the hardware itself to showcase how we have integrated different systems on the hardware. I'm happy to talk more in detail. Yeah.